When a startup bolts RAG onto their LLM, they think they're dodging the multi-million-dollar retraining bill. But look under the hood, what they've actually built is a quiet, distributed money-burning machine. In 2020, a paper introduced Retrieval Augmented Generation, a hybrid that gives an LLM a search engine to pull facts from a database before answering. The selling point was simple: instead of retraining a billion-parameter model every time new documents appear, you just upload them to the retriever. This promised to slash computational costs. On paper, it's a clever shortcut. But once you deploy it, every component carries a recurring price tag. The moment you convert a sentence into a 1,536-dimensional vector, you've started a meter running. That vector needs storage, a search index, and frequent recalculation as your data changes. And as your knowledge base grows from thousands to millions of chunks, those tiny costs compound into a significant monthly bill. Worse, the retrieval itself isn't free. High-quality nearest neighbor search requires careful index tuning and significant compute. Then, after the retrieval, you stuff those chunks into the LLM's context window, adding tokens that you pay for on every query. The infrastructure tax hides in these layers, and most teams never estimate the total before they start coding. The result? A pipeline that seemed cheap at first glance silently eats margins, query by query. That's the real cost wheel autopsy, layer by layer. That retrieval journey begins with a numeric fingerprint. OpenAI's text embedding 3 small model produces vectors with 1,536 dimensions. Each dimension is a 4-byte float, so a single embedding weighs about 6 kilobytes. That's nothing until you multiply by 1 million documents. 1 million vectors equals 6 gigabytes just for raw data. But vectors don't live alone, you also store metadata, and the HNSW graph adds its own bulky edges. A realistic index often doubles that footprint, pushing you to 12 gigabytes or more. Cloud object storage for 12 gigabytes costs pocket change, but vector databases typically need fast SSD to serve low-latency queries, ballooning the price. Multiply by multiple environments, dev, staging, production, and the storage bill alone starts to look like a recurring expense, not a one-time setup. And generating those vectors costs money, too. Embedding API charges per token. For a one-page document, you're burning a few cents, but across a corporate knowledge base of 100,000 documents, that's hundreds of dollars up front. Data changes constantly: news articles, support tickets, product specs, forcing you to re-embed. And if you store multiple versions of the same document, like historical snapshots, the index volume multiplies again. The meter never stops. Even before a single user query arrives, the embedding layer has already started extracting its tax. Few teams model this cumulative cost when they draw the initial architecture diagram. Even after you pay for vectors, you've still only built the raw materials of search. Making those vectors queryable at scale demands a nearest neighbor index, and the industry standard is Hierarchical Navigable Small World (HNSW). HNSW works by connecting points into a graph of short and long-range edges. But the magic comes with a tuning headache. The EF construction parameter controls how many neighbors get linked during graph construction. Dial it up, and recall jumps, you find more relevant results, but the index build time doubles, and the graph itself bloats with extra connections, consuming extra RAM. Then at query time, you face EF search. Higher values scan a wider region, improving accuracy but adding milliseconds per query. Those milliseconds might seem trivial, but at 1,000 queries per second, each extra millisecond costs 16 minutes of CPU time per day on a single core. Multiply by your cluster size, and the cloud meter ticks fast. Many teams never tune these parameters, they accept defaults, then wonder why recall is poor or why the server crashes under load. The real money leak isn't the index, it's the weekend spent debugging why the search is slow and expensive. Vector search alone is rarely enough. For precise keyword matches, product codes, error IDs, you need a classic inverted index like BM25. That means maintaining 2 competing search pipelines. Your database duplicates every document, once as dense vectors, once as tokenized terms. At query time, you fire both searchers, then fuse their results with a weighted re-ranker. The infrastructure tax just doubled. On a typical cloud setup, you might run the vector index on GPU-optimized instances, while the keyword index sits on CPU-heavy nodes, making your cloud bill a confusing patchwork of line items. You're paying for double the storage, compute, and a fusion layer that itself demands tuning. Debugging becomes a mess. Why did BM25 rank a document higher than the vector score? Did the fusion weights break? And all this complexity still fails on the most valuable kind of question, the ones that require aggregation across the entire dataset. Baseline RAG chokes on queries like, what are the top themes in our customer feedback, because vector search just retrieves a handful of similar chunks, not a global view. To answer that, you're forced to consider even costlier architectures. The hybrid tax is paid not just in dollars, but in engineering hours spent chasing elusive recall. Once the retriever hands over a set of chunks, a new meter starts running, the LLM prompt. Every chunk is raw text that gets concatenated into the context window. A typical chunk is 300 tokens. If you retrieve the top 5, you've added 1,500 tokens. That might be 3 to 10 times the length of the user's question itself. On a model like GPT-4o, where input tokens cost around $2.50 per million and output tokens far higher, those extra input tokens turn a 1-cent query into a 5-cent query. The chip damage compounds because attention mechanisms scale quadratically with sequence length, so processing 2,000 tokens is more than twice the cost of 1,000. And here's the irony, even with all that context, the model can still hallucinate. You're paying for tokens that may not prevent a wrong answer. Some teams naively crank up chunk count, thinking more context equals better answers, and watch their API bill quietly double overnight. The token tax is insidious because it shows up as a line item you don't inspect until the end of the month. Before you know it, your RAG pipeline is less a money saver and more a money multiplier. When vector search fails on dataset-wide questions, teams often graduate to GraphRAG, a technique from Microsoft Research that extracts a knowledge graph from the documents and then summarizes communities of entities. That extraction step is where the cost alarm should blare. To build the graph, an LLM must process every single chunk to identify entities and relationships, often requiring multiple calls per chunk. For a corpus of 100,000 documents, you might burn $500 just to construct the index, not including storage for graph nodes and edges. Then, answering a query involves multi-hop reasoning. The system navigates the graph, gathers context, and runs additional LLM summarization passes. The per-query cost easily exceeds 10 cents, an order of magnitude above simple RAG. Agentic RAG goes even further, looping multiple retrieval and verification steps, each one a separate LLM call. You're layering invoices, embedding, graph building, graph traversal, agent orchestration, and final generation. The question almost nobody asks before building is, what will my per-query cost be at my expected volume? 100 daily queries might feel harmless, but 1,000 per hour quickly flips the ROI from build to buy. The most expensive mistake isn't choosing the wrong stack, it's not modeling the running costs before the first commit. The infrastructure tax isn't a bug, it's the nature of stitching retrieval and generation.